We're in Rosen 3.3, Complexity of Algorithms. We're going to look at a couple of more algorithms and discuss their complexity by counting operations. In these, we will ignore comparisons that are inherent in the looping commands and just look at comparisons that are explicit commands. Here we're looking at the bubble sort algorithm. And recall from the bubble sort algorithm, we have a nested loop. The outer loop goes from 1 to n minus 1, where n is the length of the list that we are sorting low to high. And then on the interior loop, j, the index j will go from 1 to n minus I. So the first time we go through the loop, I will be 1, and 1 will go to n minus 1, and that inner loop will execute n minus 1 times. And the next step for the outer loop, and I will be 2, so j will go from 1 to n minus 2, so it will execute n minus 2 times. All right, what happens in that loop? We're counting comparisons, and there's only one comparison inside of that inner loop, and that's a sub j greater than a sub j plus 1. If so, we do the exchange. If not, we leave them alone. And we go to the next iteration of j. All right, so that tells us right there that we're going to have n minus 1 executions, plus n minus 2 executions, and it will look something like this. N minus 1 for the I equal 1, n minus 2 for I equal 2, and eventually 1. So that's how many times the comparison a sub j greater than a sub j plus 1 will be executed. And we have a formula for the sum of the first n minus 1 integers, and that's n times n minus 1 over 2. And if we multiply that out, we see that we have a polynomial in n of degree 2. So that tells us our algorithm has complexity of big theta of n squared. Okay, so the algorithms we've seen with a single loop of size n have a big theta of n complexity. With a nested loop, both both have functions of n, we have big theta of n squared. All right, let's look at another algorithm. This one for matrix multiplication. So remember when we multiply two matrices, A and B, the left matrix will have m by k, m rows by k columns, and then the right matrix will have k rows by n columns, so that the resulting matrix will have m rows and m columns. So there's m times n elements in the matrix, and each one of those has k additions and k multiplications, and here's where we see it. We have 3 loops. And the outer loop will step through the rows, and then the second loop on the inside will step through the columns to cover all m by m times n elements of the product matrix. And then at each step, we will do the interior loop will be q from 1 to k, where we do k additions and k multiplications to calculate the value of the entry of the ijth element of the product matrix. So that means we have k additions or multiplications for m times n elements, and that means we're going to be big theta of m times n times k. Now, what if we have a square matrix where it's an n by n matrix? In that case, we would have big theta of n cubed complexity. And that's what we say on the next slide. If they're 2n by n, we've got n squared entries. Each one of those has n multiplications and n additions, which means we have n cubed multiplications and n cubed additions. And then we saw how that one had 3 loops that were nested to give us n cubed.